So this video is going to go over how to fill in Aufbau diagrams and how to use those to make to write electron configurations for different atoms. So just as a quick vocabulary review, remember that these lines here are representing energy levels, and we represent that with the first number there, 1, 2, 3, 4. That represents a distance from the nucleus. Then we can talk about sublevels within those energy levels. You have your S sublevel, P, and then D, and they really represent different shapes. So finally, the thing to understand are these circles. They represent orbitals, which we talked about. Our quantum letter would be ML. So the S, you should notice, the S shape always has one orientation, so it always just has one orbital. I mean, you can't change the orientation of a sphere, right? So it's always the same. P is our dumbbell shape, and that can have 3 different orientations. And that's represented by these 3 different orbitals. D, remember, gets even more complicated. I'm not even going to try to draw it, but it has 5 different orientations, so we represent that with those 5 orbitals. All right, so that's your quick vocabulary review there. And so now we're going to go into how do electrons actually fill atoms. So let's do an example. We'll do beryllium, and beryllium is element number 4 on the periodic table, so it has 4 electrons. And beryllium must follow every element must follow the 3 rules that dictate how electrons fill orbitals. The first one we're going to talk about is Aufbau's principle, which says that electrons fill lower energy orbitals before higher ones. Remember, a lot of chemistry is just a game of energy, and so if it can fill lower energy orbital first, then it will. So let me actually break this rule for you so you can see what it means. So if we were doing beryllium's electrons, the first one, let's say it goes into the 1s orbital, and the second one also goes in the 1s orbital, and then the third one goes in the 2s, and then the fourth one goes in the 2p. That would never happen because we're breaking Aufbau's principle. This electron would never choose to be in a higher energy orbital when when the lower energy orbital is available. So the 2s orbital here is not full. So that's an example of how you'd break Aufbau's principle. So now I guess I shall fill it in correctly for you. So the 2 electrons are going to go here and here, and then we have 2 more, and it would fill the 2s electron. So 2 electrons can fit in any of these orbitals. The next rule we're going to make sure that you understand is the Pauli exclusion principle, which says no 2 electrons have the same set of quantum numbers. Forgive my typo here. Sorry about that. Have the same number of quantum numbers. What that really means, since we're not assigning quantum numbers, so I'm not sure that would make sense to you. So basically what it means is that electrons must spin in different directions. So this one's pretty easy to understand. It means if I had an element that the electrons would never sit like that, because that represents what we would call an upspin, okay? And if I was to draw it this way, that's what we would call a downspin. Remember, electrons are both negative, so to alleviate the repulsion that they feel from having the same charge, they are said to spin in opposite directions. So please never do this. It's going to be incorrect. And finally, here we have Hund's rule, which says the most stable arrangement of electrons is that with the maximum number of unpaired electrons. All right, so let's look at that, and I'll break that rule. Actually, I'll show you the rule first, and then we'll break it. So let's do an element like, let's do neon. So I know that they're going to fill the lower energy orbitals first, and they're going to spin opposite directions, and 2 electrons can fit in each orbital. So let me show you how they would fill these 2p orbitals. Electrons are negative, so given the opportunity, they are not going to be near each other. They're going to spread out. So how I would represent that is I would draw an electron in each of the orbitals first to show that they're going to spread out, right? Those negative charges are going to cause them to do that. And then once they're all filled, or once they're all half filled, we can then go in and start doubling up. And sorry it's so squished, but 2 electrons are in each of those orbitals, spinning opposite directions. So the order in which I did that is the correct order that they would fill the orbitals. So just to drive this point home, let me show you how they would not fill it here in blue. So definitely do this. This would not happen, okay? It would not fill 2 electrons in the same orbital because of their negative charges. All right, so why don't you give this a go and see if you can do the Aufbau diagram for sulfur. Go ahead and do that, pause me, and I'm going to go ahead and give you the answer. Well, actually, sulfur, sorry, I should start with the fact that sulfur has 16 electrons. So 2 are going to go there, 2 are going to go there, 1, 1, 1, opposite, opposite, opposite. So now I am at neon. It's going to keep going. And now I'm in the 3p sublevel. And how many electrons do I have left? 2, 4, 6, 8, 10, 12. So I have 4 electrons left. They're going to fill 1, 2, 3, and the last one is going to spin down in that first orbital. So that's a correct Aufbau diagram for sulfur. Alright, so give yourself a little pat on the back if you got that correct. The next thing that we need to be able to do is turn this Aufbau diagram into an electron configuration. So it's almost just a quicker version of this that doesn't show the sort of like the different energies of it. It just writes it in one line. So it's a pretty simple fix here. So for the electron configuration, start here, and you would write 1s2. So instead of drawing the actual arrows, we just shorten it to say, here's 2 electrons. And then I go up to the next one. I have 2s, and there are 2 electrons in that orbital. I go to the next one, 2p, count up the electrons there, and write that number as a superscript 6. Keep going, 3s, 2 electrons in it, and then finish up with your 3p because that's next, and then just write the total number of electrons, 1, 2, 3, 4. Okay, so understanding how electrons fill the orbitals is important, but then scientists get really, I guess it's unnecessary after you understand to do this a bunch of times, so they shorten it into this. Okay, but they get even more, we'll call it efficient. You can imagine how long these electron configurations might get. So scientists came up with a shorthand way of doing it. So this is the longhand way. This is called the noble gas configuration, or shorthand notation. The rule is, to do this, find the closest, I shouldn't say closest, but find the, well, I'll say the closest noble gas to sulfur that it sits within, that it has already passed. I didn't word that very well, but let me tell you what I mean. Sulfur, the closest noble gas to sulfur that it already surpassed is neon. So this is the equivalent of neon's electron configuration. And if you don't believe me, then go ahead and see what neon's electron configuration is. So instead of writing all that out, you can just basically say, hey, I'm going to start at neon and go from there. Okay, so if you find neon on the periodic table, go to the next, you're going to see it's a 3s2 and then 3p4. And so these two are saying the same thing, but this is just the shorthand version. So I'll go over a few examples here with you. It wants you to complete the orbit. It's called an orbital diagram or an Aufbau diagram, same thing. I didn't really mean to give you beryllium twice, so this should be nice and quick. Beryllium has 4 electrons. 1, 2, 3, 4. Easy enough. Okay, let's try nitrogen. You should pause me and try it yourself. because spoiler alert, I'm going to give you the answer. Nitrogen has 5 electrons. 1, 2, 3, 4, 5. Beautiful. Sodium is next. Again, pause me or else, sadly, I'm going to give you the answer. 11 electrons. 1, 2, 3, 4, 5, 6, 7. See how I'm taking care to fill them how they're actually filled? 2, 4, 6, 8, 10. Last electron goes in the 3s. Oh, and I get the question all the time, what if I drew that as a downspin? Is that wrong? No. As long as you don't have 2 electrons spinning the same way, technically it doesn't matter. I could have drawn the 1 electron like that. Generally, you see people doing the up arrow first for whatever reason. I swear I didn't mean to give you all of the answers and the examples, but go ahead and try sulfur. Here's the answer. 2, 4, 6, 8, 10, 12, 13, 14, 15, 16. All right, so some example problems here. You're going to do the ground state, which means AKA do the long version. All right? Don't use the shorthand one. So I am going to have you try these yourself. You can certainly do the whole Aufbau diagram thing. I'm also going to encourage you to see if you can speed it up and just start writing electron configurations. I usually do it by looking at the periodic table. And I think that's the fastest way to do it. So, again, I want you to pause and try all of these because I'm going to go ahead and give you the answers to all of them. So lithium is 1s2, 2s1, 1s2, 2s2. So I hope you notice S always can fit 2. And then the P has 3 orbitals that can fit 2 each, so that can fit 6. But oxygen only has goes up to the 4th element in the P block, so I know it's a 4. Calcium, 1s2, 2s2, 2p6, 3s2, 3p6, and where am I? I'm at argon, and then 4s2. Hydrogen, easiest one, 1s1. Magnesium, that's neon. Magnesium, and I'm done. Okay, aluminum, 1s2, 2s2, 2p6, 3s2, and then we have 3p1 because it's the first element in the P block. And last one, I just can't wait for these shorthand notations because they are quicker. You can see why scientists came up with this shorthand notation. 6. There we go. Alright, so now we're going to try the abbreviated one. This is the shorthand notation. It's also sometimes called the noble gas configuration. So again, if you were a little confused on this, hopefully these examples will help. Helium is a noble gas, so guess what you have to do? Helium. That's easy. Nitrogen, and by the way, I want you to pause and try these before you just listen to me do all the answers. That doesn't sound like learning. Nitrogen, the closest noble gas that comes before it is helium. And so I can go ahead and start at lithium, 1s2, I'm at beryllium, and I'm going to nitrogen. It's the 3rd element in the P block, so I know it's 2p3. Chlorine, closest noble gas is neon. So I'm going to neon, I'm filling in 3s2 with electrons, and then chlorine is 1, 2, 3, 4, the 5th element, so it has, not S, I'm in the P block, 3p5. And again, I'm looking at a periodic table when I'm doing these. Beryllium, the closest noble gas, again, is helium. I'm not even sure that's much of a shortcut after you do everything when it's all said and done, but hey, there we go. Silicon, closest noble gas is neon. 3s2, 3p, and silicon is the 2nd element in the P block. Almost done here. Barium. I did not mean to give you barium. Skip it. I'm sorry. This is a simple one, so we aren't including the transition elements. Sorry about that. All right, so that actually, I believe, wraps this up. At this point, you should be able to fill in Aufbau diagrams following those 3 rules, and you should be able to turn that idea into electron configurations by looking at the periodic table, both the long way and the abbreviated or noble gas configuration. I'm also going to encourage you to look at your NIMSY notes and follow along with Renee, because she does a similar skill that I do, and maybe she explains the rules even a bit better. So that's a totally other resource for you that I encourage you to definitely take a look at as well.